Good afternoon, everyone. Welcome to our Robotics 101 webinar, an introduction to robotics for manufacturing. My name is Matt Minner. I'm a senior consultant with technical services at Catalyst Connection. We're located in Pittsburgh, Pennsylvania, the southwest portion of the state. And along with me, I have Raminder Sandhu from California Manufacturing Technology Center, CMTC. He is the robotics practice lead, and we'd like to welcome you today to the webinar. So we'll go ahead and get started. And just a note, everyone is in listen-only mode, but feel free as the presentation goes along, if you have questions, to send them into the chat function, and we'll save some time for questions at the end. So what we're going to talk about today, that's what we all want to know, robotics and manufacturing, and we're going to hit a little bit of the why and the how. So why would we consider robotics, and you can even extend that to technology in general in manufacturing, as well as the how. What are the tools and the considerations to doing so? Next, we'll talk a little bit of differentiate between Cobot or collaborative robotics and traditional robotics, and give you an idea to help you figure out what might be right for your particular applications that you may be considering. Next, we'll take a look at some practical applications, and that hopefully will help you identify some opportunities that you may want to look into further. And then we'll wrap up by sharing a little bit about the MEP resources and support that we have to offer, just for your awareness. So first off, the MEP National Network, that's where both Raminder and I work at, and you'll see we have over 50 centers around the country, and it's part of the Manufacturing Extension Partnership, all focused on supporting small and medium manufacturing. It's a public-private partnership, receives federal funding through NIST, and many states have state funding sources as well. And again, our sole focus is supporting small and medium manufacturing in our relative areas. And you'll notice 4 of the centers there, Pennsylvania and CMTC in yellow, as well as Impact Washington and Fuse Hub in New York. And these centers are highlighted because along with Raminder and I, we have 2 colleagues from the other 2 centers that have been part of a project connecting the Manufacturing Extension Partnership, MEP Network, with Manufacturing USA, which is another map you see on the right side of the screen. Manufacturing USA is a network of manufacturing institutes that focus on advancing manufacturing technologies. And in the case of our 4 MEPs, we have been working together with ARM, Advanced Robotics for Manufacturing Institute, which actually just happens to be located directly below me where I sit here in Pittsburgh. But they are a national organization, all focused on developing the technology and workforce initiatives to help drive adoption of robotics and just propel U.S. manufacturing forward. So, where you're talking about robotics, but why would that even be something we would consider? And like I said, you can almost extend that to many different technologies in manufacturing, but so for robotics, one of the main things you'll hear quite often are the 3 Ds: the dull, the dirty, the dangerous. And if you think dull, just think those repetitive tasks where you have a human operator today doing the same task over and over again all day long. So dull, boring work. And just really not ideal for human operators, along with the dirty and dangerous. So then you start having some, whether it's health and safety concerns. So again, not ideal conditions for human operators, but those are great opportunities for robotics and things to consider. From a production bottleneck standpoint, one good example that we see often with a lot of our metal fabrication clients is making the transition from CO2 lasers, which quite often cutting was their bottleneck in the production process, and then transitioning to fiber lasers, which are just this step change in production, and especially when you combine that with these automated towers and other systems that really allow them to produce and have tons of work in process. And now it pushes their bottlenecks into other areas. A lot of the processing, welding, assembly, forming, all of which create opportunities for robotics to expand production using your existing workforce. And a number of other aspects from part traceability or needing to verify date like lock codes to the high precision and high dexterity tasks where robotics really excels because of their precision, and the areas where humans just really aren't able to do that as well. We already talked to the health and safety, et cetera. But that's a big one. Those can be the most impactful applications that can improve the quality of work, the work conditions for your employees, make them take away those tasks that you have a hard time filling. You have hard enough time finding skilled workers, let alone for the undesirable tasks. And then finally, multiple shifts. You're able to just take potential investment and spread it that much further. So a lot of different reasons to consider robotics. So anything else that you'd like to add?
Yeah, Matt. Yeah, if I could just add a couple of things. So what we typically consider initially for robotics applications are those high volume processes. So when you're making hundreds of thousands of parts per year and you're having high speed, high volume, that's where robots really excel. Another way, the corollary of that is what I call long duration tasks. So that could be, say you're welding parts on an I-beam, for example, and it may be 3 or 4 hours to complete the weld of that entire part, or a fuselage on an aircraft. There may be riveting applications or something where these aren't by any means high volume industries if we think about structural steel or aerospace. However, there are certain tasks, grinding, deburring, polishing, welding, where it takes a long time to complete that process. And those are also areas where robotics can lend itself and be very useful. And those are great applications for robots. And the other one, of course, is to reiterate, can't emphasize enough, health and safety, getting your workers away from toxic fumes, or if you're in a foundry or you have furnaces, getting them away from uncomfortable environments. So all those areas are great applications where you want to look at automating and getting people away from those difficult tasks.
Great, thanks, Raminder. So that was talking a little bit of the why. It's obviously a pretty brief overview of the why, but I think a lot of them resonate quite a bit with manufacturers, and they can identify a task or two or a few things. Man, it would be great if we could automate that, or even just a portion of it to reduce the burden on our existing workforce. So I want to talk a little bit about the how. So the tools in our toolbox, so to speak. We have 4 typical types of robotics, from the articulated robot arm, the delta and parallel, or sometimes called spider robots, SCARA units, and Cartesian, sometimes called gantry robots. And each of them have advantages and disadvantages and some typical applications, and we'll talk through that now. The articulated robot, that's when most people think of, hear the word robot, that's typically what folks are thinking of. The big automotive assembly line with many robots going to town, welding on frames, et cetera. And so that's the real typical robot. They would be dictated, or referred to by their degrees of freedom. So you typically, a fixed axis articulated robot arm is pretty typical. It means there's 6 axes of rotation for all the different joints. Sometimes you even get 7 axis robots, which a lot of times give a little that one to extra degree of freedom to do machine tending applications where you have to reach in or around objects, but we'll get to that. But you can see, if we got almost over 2+ lines of potential applications. So this by far is the widest flexibility in terms of application. You can call it kind of the jack of all trades and master of some. You know, there's a few of them where it certainly would be the best suited, but it can do just about everything. And a lot of those reasons it can is because of the flexibility and dexterity that just the geometry and the nature of the robot provides. The mounting, you know, right here you see it mounted just on a horizontal surface, but it doesn't have to be. You can mount it from the ceiling if you wanted to, put it off of a wall to, you know, reach over a conveyor or some other workspace, even mounted on a mobile cart. You know, we have clients who have fabricated up their own wheeled carts to really up the flexibility and literally take it from one workstation to another. And that's, you know, one of the benefits of collaborative robots that we'll talk about here soon. Just a lot of flexibility in mounting. You know, reach and payload has a really wide range from very small to the largest robots in the world, capable of lifting, you know, 2,000 or more kilograms. So you know, a couple tons. The downside, you know, all the flexibility and dexterity that you do get, you know, comes at a cost. The precision, you know, can degrade as you operate in the max zone, so to speak. So when you're at the farthest extent of the reach and the maximum payloads, especially at the same time, precision, you know, tends to degrade. And then you see speed there, which seems a little counterintuitive when you're talking about robotics and seeing speed as a negative. I say relative speed, because compared to other robots that really excel when it comes to high-speed applications, this, you know, articulated do not excel in that same fashion, but are certainly fast in their own right. The next stack we'll talk about is a Cartesian robot, and as I mentioned before, called a gantry robot. You see a smaller list of potential applications, but you know, still for those that it does, it is particularly well suited. The positives is it's a custom robot. You really are piecing together off-the-shelf componentry to create whatever range of motion that your application needs. And as such, the cost can be more affordable compared to similar capacity robots, just because you are using a lot of off-the-shelf componentry. Reach and payload, you know, likewise, can whatever linear actuators are used, you can really do really high payloads and do some pretty unique applications. And you know, footprint, you see it's the frame that supports it can be, you know, pretty small in footprint or even be suspended. So you know, really allows a lot of flexibility. The downside, the dexterity, just because of the nature of this type of robot, that it's all except for what may be in the wrist joint area is linear actuators. So moving in a straight line in one direction or the other doesn't allow for, you know, reaching into compartments. So say for machine tending, where you're actually pulling parts in and out of a, you know, CNC mill, for example, this would not be their ideal application. That would not be something you do with the Cartesian for the most part. On the other end, because of kind of the opposite side or the other side of the coin from custom, is doing it yourself can be a bit of a challenge, especially for those who are, you know, looking to take advantage of the ease of use of a lot of collaborative robots. This would not be in the same category per se. Would take a lot more expertise to either design and install one of these robots yourself. And that covers that. And the SCARA, which is another unique style of robot, called the Selectively Compliant Articulated Robot Arm. It's a bit of a mouthful, but essentially just if you look at each of the joints, you have two joints coming off the, I'm not sure if you see my cursor here. Oh, yeah, just the two joints coming off the mounting pedestal here. You have two rotational joints and then one linear joint. So in each of those joints, the compliance is moving in one or two directions max. So that, you know, makes it excel when you have vertical assembly applications, things of that nature. You know, pick and place inspection or dispensing applications. And where these really excel is speed and precision. They are really very fast, and have a small footprint, and can be reasonably priced as well compared to similar capacity robots. The downside, they do have a pretty limited range of reach and payload, and as we talked, the dexterity, one of the things that gives them an advantage of having very high precision, especially in that vertical direction. They have less dexterity, and it is a fixed motion path that they follow.
Yeah, Matt, just to add real quickly on the SCARA robots. So they're great for applications like screw driving or for pick and place. So you have very rapid, fast movement in the X and Y plane, and then you have that Z axis vertically. It's a rigid axis, but it's good for those types of applications I mentioned. And we'll get into some of those applications later on in my section.
Excellent, excellent. Okay, now the last of the four types we're talking about is the delta or parallel robot, also called spider robots. If say the SCARA seemed purpose-built, the delta and parallel is even more so. You see even shorter list of potential applications. When you think these types of robots, you're thinking high-speed packaging, high-speed assemblies or inspection, because part of that is just the way they're designed. That was exactly what they were built for. You see the three pods at the top or at the base of the robot, and that's actually where all the actuators are held. So that makes the linkage to actually move the end effector extremely lightweight. So just through the kinematics, the way the joints move and the linkage makes it extremely fast, really high accelerations and high speeds. So that is where it excels with low payloads at the same time. So on the downside, the reach really is in a circular area directly below the robot, and as we talked, lower payloads, and they're really very purpose built, so don't have the same extent of flexibility and mounting. It's always ceiling mounted, because 10 or 9 times out of 10, if you're seeing one of these robots, it's mounted above a conveyor, and there's probably more right next to it to help with the task that it's going after. And lastly, just not a major con when it comes to the applications that you're trying to go after, but they can have some additional maintenance to be aware of just with the moving linkages. But they excel at the applications they're suited for. And that's just a chart to help remember what the key aspects of the 4 different types of robots, and you see where they excel from the aspects of the application, whether you're looking for high speed or high payloads or precision or dexterity are more critical. You see where most of the robots fall out, where they have 1 or 2 where they excel most, and others where they're less suited. And again, the articulated arm can you could make a case for some of the other, depending on the application of it, still kind of checking that high speed and high precision box, but that's really where things shake out here, just to give you a general idea of the best suited applications. Okay, so that was really just talking through the tools in the toolbox as we mentioned, and now an additional layer above that technology is the idea of collaborative robots. That's what we're referring to as cobots previously. And the whole idea there, as the name implies, is they're able to collaborate with or in close proximity to human operators. And the way they do this is through the software and the sensing capabilities that they have for identifying when an obstruction has been hit by either feeling the force or noting that their movement has been impeded from where they expect it to be. So that's a lot of how it goes, and it creates a collaborative function. And also just by operating at lower payloads and speeds, historically, and that's a pretty short window. And then what's over the past 5 years or so, remember that collaborative robots have become more prevalent.
Yeah, I'd say that's about right.
Yeah, so it's historically in that period, they typically topped out payload right around, 10 to 15 kilograms, or so about, 20, 25 pounds. But that is starting to increase. You're seeing additional entrants to the market, and so that's starting to change. But still, in general, there would be lower payloads and speed as compared to traditional robots. Now, one key point that we want to stress is the robot. It's a collaborative robot, and it always will be. But the real question that you have to consider is your application collaborative? You're never taking a robot out of the box and using it as is. You're always adding end effectors. You're working with work pieces in a work cell with other tools and hardware. So that's really where the risk assessment comes in, and truly understanding how collaborative the application is. As soon as you add a sharp or a hot end effector, or working with a workpiece that has burrs or is also hot itself, or many different factors or possibilities, that's really where they may be collaborative, but you really have to do a complete risk assessment to understand the application as a whole. Some of the other benefits that collaborative robots have, their user interface is really intended for those, without programming experience. So they're really user-friendly and intuitive. And due to some of depending on the applications, when you're able to install with less safety guarding, you're able to achieve implementations at typically a lower cost, easier to implement, leading to a faster return on the investment that you're making. But, again, it's the application that dictates how complex that integration will be. A given application will require the same integration, whether it's a collaborative robot or an industrial robot or a traditional robot. So that's, just also something to keep in mind. But they are a great first step into robotics.
Yeah, and Matt, just wanted to add, what you mentioned about safety, that is key. We're looking at an application once where the client was considering picking and placing sheet metal. They had 1 foot square pieces of sheet metal they were going to move around with a collaborative robot. And so the issue is that, the very sharp edges, and, you do have to consider what you are moving around, because that makes all the difference in the world. You definitely didn't want an operator close by there when the robot's swinging around that piece of sheet metal. So that is key in whether or not the application is actually one that lends itself to a collaborative robot.
Yeah, absolutely. Thanks, Raminder. Now, the last slide we'll hit here to just talk further about collaborative robots versus traditional robots. This got a little bit of a comparison here. For starters, you can see in the picture there, one gentleman's pushing his collaborative robot on a cart. It's so much so that it's able to move from one cell to another, and he just sets it up as work conditions and as workforce needs dictate, as compared to more of a large fixed installation. Typically not moving around traditional robotics in that fashion, because they're going to have safety guarding or have a dedicated cell. So not only making them fixed, but also increasing the the investment that's typically needed. But then again, back to you've got high speed, high volume with that traditional robot cell. You're looking at speeds similar to human, if not a little slower than a human with a Cobot. And where you make up for that, because that may sound like, oh, it's slower than human, why would I even consider that? Well, robots don't need to take bunch breaks. They don't have to have other breaks, or don't get sick. They're able to operate. So right off the bat there, you can potentially see 15, 20% or more, just with the lack of the need for breaks, that you're able to augment your production in that sense. So then just the fast setup and the ease of use compared with some of the complexities that have typically come with industrial robotics, the difference between the reach and payload, and just the overall cost. So that's some of the other factors or the differences between cobots and robots. So that kind of concludes the portion where we talk about our our tools, but now let's start looking at, well, how do you use them? What are some typical applications? Actually, before we do that, I think, Raminder, you have anything else to add here in our Cobot?
Yeah, just a couple of points. For applications where you consider a collaborative robot are typically lower payload, a small light object you're moving around, and lower speeds. Now, if you have a need for a real high-speed robot, that's not going to be a collaborative robot. They're not designed for that. And just by way of illustrating that, the typical now with Fanuc's latest family of robots, the design life is 100,000 hours. So they're designed to run, these robots to run continuously for 100,000 hours versus the collaborative robots that are on the market today, the design life is around 25,000 hours. So that kind of gives you an idea of the difference in design and durability and what the different robots are, the applications that they're meant for. When the collaborative robots first came out, they were implemented in some high-speed applications, and they had a lot of failures in the field with bearings and some of the joints. And so they have been continuing to improve the designs and making them more reliable and robust, but they're still really meant for lower speed applications. So that's probably one of the biggest things to consider. Just the nature of being collaborative and being around human operators, they aren't meant to operate at typical robot speeds where the arm's really swinging around. That was the main thing I wanted to just talk about, the difference in how they're meant to be applied.
I think that's a great addition. Thanks, Raminder. And so I'll hand it over to you and talk through some robotics applications.
Okay, now we've wrapped up the kind of what I've called the theory part of this presentation. I want to talk a little bit about practical industrial applications, and hopefully those of you who are in attendance will be able to consider, what we've talked about on these different applications and how we can apply these robots for different processes that you may have on your factory floor. Now, the application that we're showing here is a pick and place. It's a packaging application. It's food packaging. In particular, we happen to be using an articulated arm here. Usually you'll see these with either SCARA or one of the Delta robots, and I'll show some of those examples as well. So let's move on to the next slide, and I'll show some other applications. The left is probably the most famous industrial robot application. It's welding in an automotive plant. They're not showing it here, but oftentimes you'll have one robot actually holding the chassis and moving it around while the other robot performs all the welds. So this is an example of what I was talking about before, where this isn't a high volume production process, but it is a long duration task. And this is something where robots are well suited. On the right is another welding application for a large steel member, for a structural steel type of member. We can go on to the next one. Another application where articulated arms are well suited is what I call finishing applications. Finishing includes deburring, polishing, sanding, any of those types of end-of-line processes that need to be performed on a part, typically metal parts. So the nature of articulated arms with their reach and their versatility and being able to get into those nooks and crannies really lend itself to these types of applications. Here, this is a deburring wheel that's being used on an automotive a wheel part. There's another one. Painting it's not normally defined as a finishing application, but I think of it as in that family. It's a similar type of robot motion, and they're typically always done with articulated arms just because they're able to reach around to all the parts. And one of the things I wanted to point out here, we talked earlier about when you want to implement robots, and health and safety is one of the key areas where robots will give you a great return. So if you have manual operators that are in a paint booth wearing respirators and applying paint, that's something that, if possible, you want to get those human operators away from those types of tasks. If they're painting or if they're handling toxic chemicals or any types of other harmful components in your process, we want to automate those processes. And this is where robots really can shine and give you a great return. So this kind of things, if you, any of you out there in the audience who are working in production operations, if you have these types of processes and they're not automated, talk to your local MEP center, and they can help you look at whether it makes sense to add robotics for these processes. The next one is assembly, and on the left, this is a good example of the versatility of the articulated arm. The image on the left isn't an actual industrial application, but it's a research project at a university. And they're showing coordinated motion between two robots. This is very common. It's really straightforward to do with the robot, through the robot controller and the software. But what they're showing, I wanted to show with this image is, I just liked it because it shows the reach and the ability of the robots to get at all these places. And this particular research project was doing a IKEA type furniture assembly with automation and showing that it can be done. So that's one application where we can use articulated arms for assembly. We often see SCARA robots used for assembly if it's the right type of part. On the right, you'll see printed circuit boards, a surface mount where these SCARA robots are acquiring parts off a moving conveyor and then mounting them on the surface of the printed circuit boards. This type of application, a pick and place type assembly application, and screw driving, as I mentioned earlier, those are both excellent applications for SCARA robots just because of the nature of the geometry, where they can move quickly in X and Y, and they have that rigid vertical Z axis. So packaging application, or in this case, conveyor tracking. This is where you'd want to use a SCARA on the right, or a parallel Delta robot on the left. For conveyor tracking, what we want to do is we have a machine vision system mounted over a conveyor belt, and it's acquiring images of these parts as they go by. So we're getting position and orientation information for each part. And then after the camera has acquired the image, sends that information to the robot, and the robot's tracking the movement of the conveyor and picking up these parts and then packaging them. It's a very common high-speed application that we see typically in food packaging, as these parts are coming out of an oven or some other type of food processing process. So that's a great application for a Delta robot, since it's up above, it's designed to be mounted above conveyors. And you could also do this application with a SCARA robot. And on the right, we're seeing another packaging application where we're picking parts off a conveyor and placing them in boxes. Yeah, I'm ready for the next one. Okay, thank you. Dispensing is another area where we see quite often where we're seeing robot applications. On the left, Cartesian robots are well suited for this because you can have most of the robot mechanism up out of the way. You can't see the conveyor in this picture, but you'd have parts coming in on a conveyor or some other type of mechanism. The dispensing process is done and the parts keep going on. On the right, where there's a SCARA robot. In this case, we talked about the versatility of an articulated arm. They would also be well suited for dispensing because typically these aren't high-speed applications. So that's where, again, an articulated arm would work, but we typically see either Cartesian or SCARA robots used in this case for dispensing applications. Okay. Okay, machine tending. And machine tending is getting a lot of buzz now, and somewhat has tracked the buzz around collaborative robots. In this case, you'd always want to use an articulated arm. Machine tending, for most of the applications, all the ones that I've seen at least, you have the robot's going to have to reach in and out of some kind of cavity, whether it's a CNC machine or an oven or some other kinds of process where you have to place a part inside of an enclosure. The articulated arm, based on the geometry of it and the way it's able to reach in things, it's very well suited for this. So if you have a machine tending application, most likely you're going to use an articulated arm because of the geometry. The other nice thing about this robot, the versatility of the joints, it allows it to actually, it can push all the buttons on the control panel, to turn on and off processes on the machine. You can grip the door handle of the door of your device, in this case, like CNC door. It can open the door, place the part in, close the door, press the start button. Can do all of the tasks that a human operator could do. You can accomplish with an articulated arm. Another thing on this image, and we'll get into this in a little more detail, is that if you are considering automating with a robot, one of the things to bear in mind is that once you've added that robot to your work cell, now you have to figure out how you're going to present the parts to the robot. Unlike a human operator, you can take a bin of parts, throw the parts in a bin. The human operator can pick up the blanks out of the bin and place them in the CNC machine. A robot typically will need some kind of fixturing, a part magazine, or some other method of presenting the parts to a robot in a manner that it can easily acquire each part reliably each time. There has been a lot of work on bin picking with using machine vision to pick up parts that are in a pile in a bin. That technology is still, it's what I'd call an immature technology. It has been implemented, but it's still in the very early stages. So it's yet to be proven to be a reliable, robust technology. It's still just kind of getting started. Did you have anything you wanted to add to this, Matt?
Yeah, I think, and along the lines, I think that bin picking is a good example too of, kind of the different levels of, where you can, you install a robot cell on day one, and it doesn't mean it's going to always be the same. A lot of times you start, what's that first step in getting something installed? And maybe at first it's a tray, like you see here, a fixture, and it's sticking out of the fixture. Then, maybe it moves on to, another system. It's constantly evolving because, the advantage with a fixture like this is the robot doesn't need to see it. You can program in, work through arrays, and you have it in a set spot. It knows where it's going to be, so it can just go there. As opposed to, like when you get to that level of bin picking, now there's an additional level of perception that's required, adding vision systems, additional integration, i.e. additional cost. So there can always be a progressive approach for robotics installations where you start at kind of one level and then, work your way up. And I think the other aspect along those lines, you don't always have to automate 100% of a process. It's hard to see what may be the case just with these photos, but, think into that grinding cell or the buffing one, there could be, you do 80% of the work, so it takes some of the taxing work off the human operator, but maybe they still come in to do the final inspection and final touch-up. So there's that consideration, too, of not just what application, but maybe how much of it. So just a couple other thoughts in that respect.
No, that's a great point. And, back to it reminds me of a couple of things. Yeah, for the finishing applications, if you're doing a polishing or deburring or sanding type of process, and it's a long duration process, that's a good point. Maybe you can do 80%, 80, 90% of the work. Say you have a big fiberglass panel for an automotive application. You can do 90% of the sanding with a robot. And then the inspection, the last 10, 20%, you come in with a human operator. And again, the great thing about that is you really limit the human exposure to the dust and the other contaminants that are released when you're doing those types of finishing applications. So it's a kind of a win-win. One thing that, Matt, you reminded me with the fixturing, if we could just go back to that last image, in this case, you have an 8x8 array of parts. And the nice thing about this fixture, if it's well designed, you don't need any additional sensing for the robot. As you mentioned, you don't need a vision system to locate those parts. You can just turn the robot, you can load up the magazine, and you're going to assume all 64 parts are there, and have the robot run through that cycle of picking up each part, placing it in the CNC machine, and then putting the finished part in an output tray. That greatly simplifies your overall application and the time it takes to implement it. So those are some considerations we'll get into in more detail, but that are very different when you're looking at human operators versus a robot, and how much you have to prepare the parts for the robot to be able to work with them. The next application we're going to talk about is palletizing. This is another very common application for robots. It's starting to see a lot more use worldwide. And typically we'll only see articulated arms and Cartesian robots for this application. And that's because of the reach and the payload for most of these. These are both high reach, high payload robot designs. An articulated arm can typically, it's very common to see articulated arm robots with payloads of 25 kilograms, even up to 100, 200, as Matt mentioned, 2,000 kilograms. So, if you have these large, whether it's large boxes or bags of material, whatever it may be, you get the right end effector designed to acquire the part. This is a very straightforward application for a robot. On the right, just wanted to mention for a Cartesian, or we call it a gantry robot, again, the mechanism itself is up out of the way. It's above the work envelope. So it really lends itself to building conveyors and other things to bring the parts underneath. And then it's easy for it to acquire these are heavy, 75-pound rolls of film, something that's very well suited for these types of pick and place applications in the palletizing world.
Yeah, and just to note that as we were talking earlier on the Cartesian, just look at the scale of that robot, maybe, a lot larger than you may even have thought that Cartesians would get, but, essentially, a small bridge crane that it's working with. So they really, the custom nature and the capabilities, I think, are really on display there.
I mentioned conveyor tracking earlier. This is just another few examples. It's very common in food packaging, electronics, other types of consumer goods packaging, where we see a lot of parts being moved around the plant floor on a conveyor, then they have to be packaged. So if you remember what we talked about, different arms, there's two types that are great for these applications: the Delta robots and the SCARA robots. They're very fast in the X and Y plane, and they're made to pick up parts in Z and quickly deposit them. So at this point, it should be pretty clear to everyone and evident that these are great. This is a SCARA and Delta robot area, as a contrast to the previous one of palletizing, which is more of an articulated arm and Cartesian area. So to summarize, just what we were talking about, Matt had originally spoken about the articulated arm and the jack of all trades and master of some, and you can see that in that left column. It is a highly versatile robotics design. It's not the fastest robot. Doesn't have the highest payload. It is high payload, not the highest, but it is adequate for most of your applications. So that's where you'll see that with this graphic here. For most high-speed, low payload applications, you're going to want either a SCARA or a Delta robot. And finally, the Cartesian mechanisms, typically higher payloads. They can be fairly precise, but typically higher payloads. Usually lower speed applications are where the Cartesian gantry mechanisms will be most ubiquitous. Yeah. So when we're talking about implementing robots, people who are, if you haven't done a robot implementation before, it can be easy to underestimate the complexity of the task. Now, the robots can be very well designed. Robots have been around have been used in industrial applications since the 70s. So it's, we're looking at close to 50-year-old technology. However, it's the end effectors where most of the complexity comes in, and that's where you have to take careful consideration of whether a robot is right for this application. We think about what robots are doing. They're emulating human tasks. Machine vision emulates human vision. Robots emulate human motion of picking and placing and manipulating objects. However, in spite of all the technology we have available to us today, we haven't come up with anything close to the versatility and dexterity of a human hand. you think about it, you can pick up a piece of paper, you can pick up a needle, you can pick up a brick, you can pick up a bag of saline solution. All of those things are very easy and straightforward for a human operator to do. Now, if you asked a robot to do those four tasks, there doesn't exist today a single robot gripper that can accomplish all of that. So that just gives you an idea of the consideration needed for end effector design. It's crucial and vital. There are a lot of different alternatives for solving those types of problems. There's quick change end effectors that the robot can change out itself as it's working, depending on what the application is. There's 2 and 3-up end effectors where, depending on how the end effector is, which direction it's pointed, it'll give you different capabilities. But that is something to consider, as we've yet to really simulate the versatility of the human hand and the ability of humans to sense what they're holding and how much. A great example of that is like when you pick up an egg. A human being would never pick up an egg and just crush it because it's applying too much force to it. Your hands are in a constant feedback loop, sensing how much force you're applying to an object, allowing it to slip just slightly. There's small micro slips that your hand is allowing to do, so that you're not exerting too much force, you're not wasting energy picking it up, but you're applying just enough force to the object that it doesn't fall out of your grip and not too much to crush the object. So we haven't been able to duplicate that high speed closed loop feedback mechanism with robot grippers yet. There's a lot of research being done around that now, but that technology isn't out there yet. So this is something we can't really emphasize enough. It's a key component of when you are designing a robot work cell is end effector design. Is there anything you wanted to add to that, Matt?
No, I think you hit it, Raminder. And so, really it's the robot is the kind of the easy part. It's everything that starting with the end effector and moving on to everything around it, because you're not going to have that in a bubble. It's going to be in a cell, working with other hardware and tooling and sensors. And, as you start to see this, you can start to understand why typically you look at the cost of a robotic implementation, and it's, 2 to 3 plus times the cost of the robot hardware itself, because of all these different factors and all these different considerations. So that's, it's not just the robot, it's the whole cell.
Yeah, exactly. And that's a key thing to consider. Is like, let's say you have a $50,000 robot, the hardware itself, the robot and the controller, your robot sales guy comes out and says, yeah, this is a $50,000 piece of equipment. When it's all said and done, once you've added all the sensors, once you've had a systems integrator, or you've done the programming yourself and you've written the code for the robot, and maybe you've added a vision system, you're definitely going to need to add some type of mechanism to feed parts to the robot, whether it's a flexible feeder, or a vibratory bowl feeder, or conveyors. You're going to need some sensors to tell the robot that part's in a position ready to be picked up. Then there's the end effector design. What type of end effector are you going to use? It's communication with the other equipment on your floor. Once you've considered all of these, easily you can triple your budget. So your $50,000 robot has suddenly become a $150,000 robot work cell once it's been properly programmed and all the equipment has been installed around it to allow the robot to do its job.
Okay. Well, just before we wrap up our webinar here and take a few questions, just wanted to highlight from an MEP standpoint in the Manufacturing Extension Partnership, the resources that a lot of MEPs like Catalyst Connection, CMTC, Fuse Hub, and Impact Washington are working with. There's a lot of different resources such as working groups or provider networks to help you navigate, exploring robotics or other technologies. A lot of times there's grant funding that may be available, training or conduits to ARM and other institutes, in addition to project services that are frequently offered especially towards the front end of a project, or assessments, application evaluations, or even helping you walk through the range and bringing forth proposals from different integrators in your area, and just helping you navigate that whole process. So definitely something to consider. So with that said, if any of these opportunities look familiar, please reach out to us. I've got contact information for Reminder and myself, along with two of our colleagues in New York and Washington, up on the screen. And if you happen to be from another area outside of one of these four states, there's a link also to go to the NIST MEP website and identify what MEP is close to you, or if all else fails, certainly feel free to reach out to us and we can help you as well. So with that said, we'll take a look here and see what questions we have. Okay, so let's see, we got about the pricing considerations. Let's see, so they're indicating universal, universal robots. You certainly see those a lot in most trade shows, pretty much anywhere, regional, national. You see them in the 20,000 plus range. It's pretty, from their smallest end is, I think, to 20 to 30, upwards of 45 to 50 or more now that they have the UR16, 16 kilogram unit. But this individual indicates they had saw a much more inexpensive robot. Let's see, Robotics Cobot at $1,100 of it. You need an engineer to assemble different parts. And so I say, essentially, are you seeing the cost of cobots coming down? What sort of comments do you have? Well, what have you seen, Reminder?
Yeah, the cobot and robot pricing is coming down. Now, there are SCARA robots. Epson makes a SCARA robot. It's a $9,000 SCARA robot. It's a very low payload. It's about a pound, 2-pound payload robot. It's a small reach. It's a very robust and reliable. That's another 50,000 hours design life robot. I don't necessarily want to limit the talk to cobots, but whether we're thinking of cobots or traditional robots, prices are continuing to drop. So they are, for typical applications, a standard size cobot, like say a universal size, they start at 3 kilogram payloads, and I guess they're up around, what did you say, Matt? Now there's a 15 kilogram payload one. Those are in the $30,000-$35,000 price range, and then they go up from there. But we are seeing some new entries, some startups, some smaller companies that are introducing cobots and robots at the sub $20,000, so it's in the $10,000 to $20,000 price range. So it is happening as the technology matures. We are seeing pricing continuing to fall. You do still have to consider the other implementation costs, and I think despite what the cobot manufacturers say about ease of use and that you don't need as much in terms of safety cages and light curtains and other things around the robot, you're still looking at least a 2x or a 3x factor once it's all installed and programmed and ready to run.
Okay, so do we have any other questions, Allie? Oh, let's see. Someone asked if a copy of the presentation will be available. And yes, here in the coming days, we'll distribute a copy to all the registrants, and there will also be a recording coming out in that same email, right? A recording of the session if you missed any of it. So that'll be sent out to all the registrants, and will also be posted on most of our MEP website, our Catalyst website. We'll have a link there as well. Let's see here. Are you aware of any robots used in the chemical processing, metal finishing industry? Let's see. Chemical processing, I don't know if they're referring, I know there's some chemical machining processes. I depends if that's what's being referred to here. But does that chemical processing, metal finishing industry, some sort of, do you have an idea on that, Remember? Plating and, okay. They clarify plating and anodizing. So there's like dipping.
Yeah, so it would be a pick and place type of application where you're typically dipping parts into a bath, chemical bath. And so, yeah, that would be an articulated arm typically, or it could be, actually any of the mechanisms, even a Cartesian or possibly a SCARA. But most likely that would be an articulated arm application. So, yep, there are cases of that. The main consideration is end effector design. There are washdown, for example, there are washdown robots that are used a lot in food processing, where you have positive air pressure on the inside of the robot so that you can completely wash down the robot and without damaging it at all. So that would be a potential robot mechanism that you would use for if you're talking about chemical finishing of parts.
Okay. Well, I think that looks like all the questions that have come in here. So again, we're just about the top of the hour. So thanks everyone for, one more. How about assisting racking parts? And that was with the same application of plating and anodizing. And I think, certainly it's obviously, hard without seeing the application, but of racking parts, taking things that are coming, whether it's down a conveyor or transferring from some other process or other tooling, to place parts in a known location. You see a lot of them used in the powdered metal industry for feeding furnaces, having parts coming down a conveyor and either putting them, or in ceramics, putting them in saggers to go through a furnace. So I think certainly the assisting, and if that's implying working with a human operator, there's a lot of work going on in that space as well, but certainly more development to come there.
Yeah, and I think the main thing, as we mentioned earlier, for racking the parts is going to be the end effector design. You'd most likely, again, go in an articulated arm. So the robot mechanism is there. You have a wide variety of sizes and payloads to choose from. Just a matter of getting the correct gripper design so that you can handle the largest number of parts. If you have a high mix of production parts, you're going to have to be very clever with your end effector design, or do quick change end effectors so that you can adequately pick and place all the parts that you want to rack.
Yep, absolutely. All right. Well, thank you, Raminder, for joining me this afternoon to go through this webinar, and thank you to all those on the line for registering. And I hope everyone has a great afternoon. We'll be sending things out shortly. Thanks again.
Thank you, everyone. We really we're real nerds when it comes to robots. We can talk about this all day, so we appreciate the opportunity to speak on this, and we thank you all for attending.